Whenever you're ready, you want to start?
Yes, thank you.
It's a pleasure to introduce Trevor Wooley here and also at Purdue University, who will tell us about beyond translation-invariance in harmonic analysis, arithmetic harmonic.
Thank you. So I know I'm not the most powerful mathematician because I did not arrange a snow day today. Like some of my colleagues. Okay, so it's a pleasure, of course, to be here. What I want to do is to give you an impression of some recent developments in between analytic number theory and harmonic analysis that have actually kind of an algebraic flavor in places. And this will be quite impressionistic in places because the technical details will bog us down a bit, but at least I hope to give you some idea of what's going on. So roughly speaking, the talk divides into 4 parts. Some discussion of some of the objects in the title, translation-invariance, exponential sums, and Vinogradov's mean value theorem as an example of what's going on there. And then I want to emphasize the very recent developments, which is moving beyond this important property beyond translation-dilation invariance. And then I'll fill in some of the details that I've skipped over involving efficient congruencing and connections with decoupling, and also a sort of stimulating function field interpretation for what goes on, which is not the usual function field that you would expect. Maybe. Okay, so this is supposed to be a colloquium, and I know we've had instructions and maybe even complaints that things should start simple. So, in the beginning, there was 1, 2, and 3. This great schism in the mathematical world, you know, what a natural number is. Okay, so everybody's with me so far, right? Good. Okay, so let me make some other deep observations. So 2 is the average of 1 and 3. So in fact, 1, 2, and 3 give you a solution of the equation x minus 2y plus z equals 0. Profound stuff, right? Well, I can get other solutions as well very easily. So that's a homogeneous equation. So this is dilation invariant. So I can multiply by the same factor everywhere, and we still get a solution. So, for example, with 10 or any other number, because I didn't tell you what base I was working with. So there you go. So that's dilation invariance. And I can also, by the way, add the same number to every one of these entries, and it's still a solution. So 17, 27, 37 is still a solution, for example, but I could translate by any single number there. So, so this tells us something about what I mean by a translation-dilation invariant system of equations. So here is just a very simple example. So I can cook up other examples which have the same property. So for example, x plus y plus z minus 3w also has this property. And well, it's homogeneous, so the dilation invariance comes for free, doesn't it? But the key property for this linear equation is just that the sum of the coefficients is 0. 1 plus 1 plus 1 minus 3 is 0. Great stuff. Okay, so this is not a talk about linear equations. I don't like teaching linear algebra, so this will be about nonlinear equations. So here's a nonlinear translation-dilation invariant equation. So this one happens to have squares and a linear equation. And just so we're on the same page, we can check that it's translation-dilation invariant. So of course it's homogeneous. Both equations are homogeneous, so it's automatically dilation invariant. And the translation invariant comes if you just apply the binomial theorem here, right? So, here we have an expansion of x plus a squared in disguise, right? So I get a quadratic part plus 2a times the linear part. And I ran out of room for a squared occurring lots of times, but I think we can do that one in our head, can't we? So a squared plus a squared plus a squared minus a squared minus a squared minus a squared is 0. Good. So you can see here that when I make this binomial expansion, the linear polynomial already appears inside the equation, so it automatically vanishes. And the same with the quadratic equation. So this is indeed telling me that this quadratic equation in the shifted variables, again, is satisfied. Sum and difference is 0. And of course, the linear equation is much simpler. So, so in fact, this pair of equations is translation-dilation invariant as well. Okay, so you can, of course, extend this idea to systems with higher degree. And that's what I've done here. So there's a system of equations. Every one of the degrees, 1, 2, up to k, occurs in this system. And the same kind of binomial expansion argument would convince you that this is translation-dilation invariant. And this was a system which was studied by Vinogradov in the mid-1930s. It occurs also in work of Mordell in 1932 in the finite field situation. And this translation-dilation invariance plays a key part in the arguments that, well, that Mordell used in the finite field situation and Vinogradov used in the situation of the integers for bounding mean values of exponential sums. So that's another one of the components which occurs in the title and is the subject of this talk. So I'm using the usual notation from analytic number theory. E of z is e to the 2 pi I z. And I have this exponential sum with coefficients alpha 1 up to alpha k, and all of the monomials x up to x to the k occur here. And if you expand this all and use orthogonality, then you find that this is counting the number of solutions of the system of equations which we have at the top of the slide here, with variables between 1 and x. And if you've never encountered this kind of thing before, one of the key little tricks here is that the conjugate, complex conjugate of the exponential sum that you see inside the absolute values is just the same exponential sum with the arguments alpha I switched to minus alpha I, just the conjugate. So, so this really does amount to an orthogonality relation. And we'll see a little bit more about this later on. Right, so you'll notice that I don't have many pictures in my slides. So when you see a system of equations like this, Diophantine equations, in my head, this is a picture. This is like, ooh, a big system of equations. So anytime you see a system of Diophantine equations, you should think of this as a fantastically illuminating picture. Right? So, okay, so so what have we seen? We've seen translation-dilation invariance and this Vinogradov mean value theorem. But the importance of the progress on Vinogradov's mean value theorem, I have to try to explain to you. So let me talk a little bit about related mean values of exponential sums. And maybe the starting point is this very simple example of a quadratic exponential sum. So if I look at the exponential sum over squares, so again, there's an orthogonality relation here. So this is counting the number of solutions, if s is an integer at least, a positive integer, counting the number of solutions of a simple Diophantine equation. Not a very impressive one, so you don't have to be impressed by this. But you see, it has a nice symmetrical format, and we can think about lower bounds for the number of solutions of equations like this in a very concrete way. So if I want to understand how many solutions there are, then there are two fairly obvious contributions. One is where these variables x1 up to xs are just a permutation of the variables on the right-hand side of the equation. So since these variables are all in a box of size capital X, and the number of choices is going to be of order x to the s, actually closely asymptotic to something like s factorial x to the s. Not quite because of coincidences, but so there's certainly a contribution of size roughly x to the s to this mean value, which I can't escape. And there's another contribution as well, which actually corresponds to a product of local densities in this problem. Just as a crude lower bound, you can see that there's a contribution of x to the 2s minus 2 just by looking at a tiny neighborhood of alpha equals 0 in this mean value. So if I look at alpha at most as big as 1 over 100 capital X squared, then the argument of the exponential sum, 2 pi I e to the 2 pi I alpha x squared, so 2 pi I alpha x squared is very small. And so there's hardly any cancellation in the sum at all. And if you had 10 seconds, you could jot down on the back of an envelope a little argument which would show that the contribution from this exponential sum is pretty close to x to the 2s on this set of measure roughly 1 over x squared. So automatically there's a lower bound which has size x to the 2s minus 2. And for any positive value of s, one can prove this. Even the x to the epsilon can be improved if you want to. And this is sort of a very classical problem. More than a century ago, this sort of thing would have been known using divisor sum type estimates. So somehow squares are very special. Linear equations are very, very special. Squares, you know a huge amount about, quadratic equations. And so we're going to be in the business of trying to think about higher degree equations. So I think, you know, the great explorations of the analytic theory of Diophantine equations, exploring linear equations is exploring what's sitting on your desk in your office. Exploring quadratic equations is exploring what's inside your office. And high degree equations is like going to Antarctica. And if you use your office equipment in Antarctica, it doesn't go well. So anyway, that's what we'd like to do, is to think about higher degree equations. And as I'm hinting at, the knowledge about higher degree equations, except in very special situations with group structures, divisor sums, very not normal exactly contrived situations, but situations with special structure, the knowledge in general was quite poor until very recently. So that's why Vinogradov's mean value theorem was of such interest. So that's what we encountered a moment ago with these translation-dilation invariant equations. So already in the middle part of the last century, this was somewhat special. So one could get upper bounds which almost match the conjectured upper bound. And this is what you would get by considering a lower bound of the type we just saw with squares. So almost match this upper bound, but there's some sort of error in the exponent. Errors in exponents are not good. That's kind of really destroying your estimates. But at least this error gets very small as the number of variables, as the parameter s gets large. So in fact, you can bootstrap this. So if s has order of growth a suitably large constant times k squared log k, then you recover this conjectured estimate. And that was already known, as I said, in the middle of the last century. And in many other problems of similar type, the kinds of estimates where you match those that are conjectured, that was only achievable with a number of variables which was growing exponentially in terms of k. So this was already somehow quite close to an optimal situation. And that was the state of the art until something like 2010. So these estimates, I'm not going to go into applications, but these are vital tools in describing the best known zero-free region for Newman zeta function, Waring's problem, equidistribution results, and so on. Basically, any problem where you have Fourier series where the argument of a Fourier series can be approximated using a Taylor expansion, for example, by a polynomial, you stand a chance of using these estimates from Vinogradov and people we came after. So the big news, which looks like little news when I present it on the slide, is that this conjecture is known to hold now. So this is something which developed in the period from 2010 to 2016, 17, 18, 19, something like this. So it was first proved, first of all, the log K disappeared in 2010, and then the qubit case was resolved in 2014, and most of the critical range for general K, when a small gap was covered by the Bourgain and Demeter and Guth, which gave you the whole conjecture. And then a little while after that, I showed using these efficient congruencing methods, which I'll say something about, that you can recover the full conjecture using these, well, really p-adic methods. So there's a whole story here. And the upshot is that we now have optimal mean value estimates for the quadratic case, which I talked about, and this Vinogradov system of equations, this Vinogradov's mean value theorem. And that's it, right? So, so of course it's great. We have this giant family, this Vinogradov system, which is useful in all kinds of places, but somehow we're still very limited. Okay, so just
Why is it called mean value?
so there's a mean value, well, for two reasons actually. There's a mean value of an exponential sum here, so we're averaging this exponential sum moments. But also somehow this label got in some ways misapplied because Vinogradov used mean values of this, well, this kind of mean value of the exponential sum to study L infinity bounds of the exponential sum where the alphas are not well approximated by rational numbers. And to do this, he actually used the mean value theorem from analysis that everybody talks about to convert the sort of L infinity, well, the moment information to L infinity information. So it's sort of two reasons, but
In
sometimes the label called.
terms of the zeros of zeta,
Yeah.
the dependence on the constants, I think is
Yeah, it's critical. And
that's
yeah,
that hasn't been.
no, and in fact, the old method is superior to the new method in that respect, which has caught out certain people. I encountered a student from UCLA who had an advisor you can guess at, who had been assigned the task of using these new results to improve the zero-free region. Yeah, I mean, everybody knows, well, many people know you can't do that. So anyway, whatever. Okay, so yeah, so I was going to go on this way. So I don't want to give the impression that this is too specialized. So the same methods, decoupling and efficient congruencing methods, give you information which looks much more general. So you can study not just consecutive powers, n squared up to n to the k. You can look at any polynomials you like, and as long as they're sufficiently independent, so we have a non-vanishing Blonsky condition, then you still get good estimates, good mean value estimates, even if you have arbitrary complex weights sitting around. So this is a sort of a fairly general tool. And the important feature of these estimates is that the moment estimates you get give you something resembling square root cancellation up to this limit of k times k plus 1 over 2, where k is the number of independent polynomials that you have. So if you have consecutive powers, n squared up to n to the k, you've got k independent polynomials, non-vanishing Blonsky, and so you get square root cancellation up to this limit, and that's enough to give you the whole conjecture which I described earlier. So the two sort of competing tools.
Is there conjectured asymptotics for some of these?
Yeah.
Don't put the epsilon.
In this kind of thing, of course, that's difficult because you want such uniformity. But you certainly get asymptotics in the Vinogradov mean value theorem work. And it was known how to do that in principle going back to the 1940s, given that you have the mean value estimates themselves. there's not really a mystery there. Yeah, so I just wanted to say that, the sort of two approaches to this, which are actually the same approach, I think. So the analysts think of the decoupling approach as being a real analytic approach, and the initial arguments involve multilinear K estimates. It looks very real analytic. The efficient congruencing approach is just a p-adic approach. And you realize with this p-adic approach, which sort of both predated and postdated the real approach, that all that's going on here is that you have a discrete set of points in a valued field, and you want to have suitable characters to detect orthogonality. And if you have such a situation, then you can get these, the analog of efficient congruencing to tell you about these mean values. Now, the reals are Q infinity, it's the infinite place, so it's a little bit messier dealing with that situation because you don't have this nice graded structure to the reals. You have to make some choices, but it's really the same approach, and so you can handle many situations. And in fact, in the paper where I described how to prove the main conjecture, I sort of tackled the number field and the FQ of T for large characteristic situations kind of for free. You can deal with small characteristics as well. It's just slightly different. Okay, so that's sort of the state of the art. And I wanted to hint at what goes beyond that. That's kind of a point of this talk. So this is a new case with optimal estimates. And you should not get your hopes up too much. In fact, you might have difficulty spotting the difference from the Vinogradov approach. So the difference is that we're starting this exponential sum with the square term, not the linear term, right? Which makes it harder, by the way, because this is not corresponding to a translation-dilation invariant system. So when k equals 2, it's yet another proof of a quadratic mean value. Fantastic. But when k is bigger than 2, this is brand new. And it's the only other situation that we know somehow with these monomial type exponential sums where we get optimal estimates. So it's, even though you might not be feeling impressed right now, maybe at some point you'll feel more impressed on reflection. I mean, it's genuinely a new case. And I want to sketch out some of the ideas involved in proving this.
So if you remove the linear term, you're sort of destroying the translation invariance.
Yeah, and that's, if you think of a binomial expansion idea, when we made that binomial expansion, the linear term really appeared in the binomial expansion. So if it's not there, then we destroy a little bit the translation-dilation invariance. And actually we'll see how that can be useful in some sense to us in a moment. So, I should say, what's this funny number here? It's the sum of the degrees of the terms which you see in the exponential sum. So this really is what you conjecture to be the case. So I should say that some knowledge of what goes on in the situation existed before. So if you think about the previous slide, I had this Strickhart's type estimate, which was right here. So this doesn't care what polynomials you're looking at as long as you've got k of them. And in this exponential sum, which we're now looking at, we've got k minus 1 monomials. So in fact, you get square root cancellation for free up to a half times k minus 1 times k minus 1 plus 1. So, which falls short of the range of S you would need to cover to recover the full conjecture. So that kind of comes for free, and it's, well, in the harmonic analysis community, they would talk a lot about these decoupling results coming from curvature. And that's really, it's kind of, in hindsight, it's very much a nested linear algebra sort of result. So you're not using any number theory really to get at this result. And then I had some work with Julia Branders from almost 10 years ago now, which extended this range. And some of those ideas are related to what I'll explain. But yeah, anyway, it still falls far short of the full range. Okay, so that's 4 parts of the introduction. That's good, isn't it? Now, it's complicated writing down all these equations, so I'm going to concentrate on a very special case, k equals 3. So this already, you can see what ideas are involved, and we don't have to write too much. It's on the transparency on a slide better. Okay, so a concrete application already of this result is about quantitative aspects of solubility of pairs of diagonal equations, one of degree 3 and one of degree 2. And this has a special place in my heart because this was my PhD thesis topic given to me by Bourgain in 1988. So I finally solved the problem almost 40 years later. So 11 variables are enough to give a quantitative Hasse principle. You get weak approximation as well in this problem if you have 11 or more variables. And in fact, there are no local obstructions to solubility with 11 variables, and there are with 10 variables. Okay, good. Okay, so that's a little sort of taste of what you can do. So what about the ideas here? What about this absence of translation, dilation, invariance? So here's the exponential sum that I was kind of examining in this special case. And here are some pictures, right? Systems of Diophantine equations. So we're going to be interested in the 10th moment of this exponential sum. By orthogonality, it's just counting solutions of a nice pair of Diophantine equations in 10 variables, all the variables in a box of size x. And we already had a question about what's going on with the absence of this linear equation. So I can convert this into something which looks a bit more like the Vinogradov system if I just add in a linear equation. And the thing is, I can't just add in extra equations for free. I've had a colleague who I had to spend a long time convincing that this is not allowed in mathematics. This sends you straight into one of the inner circles of hell. So you have to make sure that you actually deal with this extra equation properly, right? So what I'm going to do is I'm going to make sure that I sum over an auxiliary variable, h, and make sure that I insert enough values of h so that it doesn't matter what choices of the x's and y's I put in, whatever this linear polynomial happens to be, I make sure that there's an h which will detect that. All right, so if I make sure that all these, if I sum over a range of h where the absolute value of h is almost 5x, it covers all of the possibilities here for sure. So in fact, if I count all of these solutions for what I'm interested in, it's exactly the same number as counting all of these solutions with this extra variable h. And now you see if I shift all of these variables, this is where the linear equation plays a role. If I shift all of these variables, binomial expansion once again, well, the linear equation doesn't change at all because I'm adding in and subtracting the same number of copies of z. The quadratic equation changes slightly because there's a sort of a 2z times a linear expression in terms of the x's and y's which appear. And so if I'm careful, I get a 2hz appearing on the right-hand side. And similarly, a 3hz squared coming from the a binomial expansion of the cubic term. And again, this is coming from the linear equation secretly. So when I study the number of solutions of this equation, for each fixed choice of z, it's counting exactly the same number of solutions as I'm counting here for this equation, for a fixed choice of z. And moreover, the variables, the shifted variables, still lie between 1 and 2 times x. So if I just relabel the shifted variables, I'll call it x1 to be expedient still, and make sure that I sum over variables in a range of size 2x, which we'll see on the next slide, then for each fixed z, this is an upper bound for the number of solutions that I'm interested in. So this mean value for each fixed z is bounded above by the number of solutions here. And then I can average over z. There's no reason not to. So if I do that, then I get to average over z, means I get to divide by capital X, the number of choices for z. And I work in the circle method. So anytime I see a Diophantine equation, I like to write it in terms of exponential sum. So what I did here was to write down an exponential sum encoding the cube, square, and linear term, involving the x's and y's, 10 copies of that. And then there's this fancy exponential sum k, which takes account of the stuff on the right-hand side there. So that's a mean value which gives me a count of all of the solutions of that giant system of equations at the top. As I average over all the z's, and because I'm averaging over the z's, I get to divide by x. So we've converted one problem into a maybe more complicated looking problem, but there's an extra variable here, maybe even 2 extra variables, depending on how you count it. Wishing analytic number 3 makes you optimistic when you're averaging over more. Okay, so what do you do with this? Well, one idea would be to apply Holder's inequality, maybe. And the reason you might choose to apply Holder's inequality to look at a 12th moment of G is because we have this optimal version of Vinogradov's mean value theorem in the cubic case of the 12th moment.
Find us again what the G and the K is.
Yeah, so the G and the K exactly on the previous slide, maybe I should have indicated. Right, so G is a cubic Vinogradov sum. So it's x cubed, x squared, and x. And K is capturing these hz squared, hz, and h terms. They'll reappear. So, right, so that is a good question. So this G is cubic Vinogradov exponential sum. So a 12th moment we've got optimal estimates for, which is relatively new. So we're automatically attracted to this because this somehow captures this, but the biggest moment where we still have square root cancellation. And in 2014, at least, the best I could do was get a 6th moment of this more complicated exponential sum that's not got square root cancellation. Each copy of K has 2 variables, h and z. So a sort of trivial estimate is roughly of size x squared. So this is not quite square root cancellation, and this is what I wrote. But at the time, actually that's good enough already to get this result for the cubic and quadratic equations in 11 variables.
So what happens if you take it's a simultaneous equation, if you use the delta method, 2 delta on this problem?
On this guy.
On your thesis problem?
On my thesis problem. Yeah, so because you've got simultaneous equations, automatically the delta function method becomes much less efficient.
Yeah, I know. And with these recent,
because there's a cubic term in the, I mean, roughly speaking, what happens? I'm
just talking about these recent applications.
It's not even quite clear to me.
2 equations.
Not even quite clear to me you beat trivial cancellation. because, I mean, things really go bad. So the new delta function method material will handle two quadratics just about, kind of inefficiently, but it's still already kind of interesting. One cubic it handles somewhat interesting. A cubic and a quadratic is just like blowing it out of order. You know, it's really, yeah. Because the height of the rational approximations grows too quickly with simultaneous equations. Okay, so anyway, this is not what I came here to talk about. I mean, I wanted to show you how you really get these optimal estimates. So let's get on with that. And it's a bit of fun, so that's why I wanted to talk about it. Because there are lots of pictures, meaning systems of Diophantine equations. So here's what the sixth moment looks like. You know, it's a system of Diophantine equations. What's not to like about that? I mean, it's kind of neat, isn't it? So everything is linear in the H's and at worst quadratic in the Z's. And you'd think maybe that's not so hard to understand, but it's not translation-dilation invariant. Sorry, something went in this there. Here we are. Not translation-dilation invariant. It's got some translation-dilation invariance. If I just shift the Z's along for a fixed choice of the H's, if I put all the terms on one side, you know, you can see that the sum of the H's minus the sum of the other H's is 0. So it would be partially translation-dilation invariant, but it's not translation-dilation invariant in terms of the H's. So it's not amenable to these decoupling ideas and efficient congruencing ideas by itself. And so one idea you might try to use, it's a natural idea to try to understand the solubility of a number of solutions of systems of equations like this, is to add in extra equations to make the two systems together translation-dilation invariant. And if you play around with this kind of thing, you see that what's kind of key to making translation-dilation invariance is that you want extra equations which kind of encompass the partial derivatives of each monomial term. That's sort of what comes out of binomial theorem, Taylor theorem, Taylor expansions. And so adding in these three equations is certainly enough to make translation-dilation invariance. I could omit the cubic equation, and in some versions of a talk like this, I explain what happens there. It doesn't work. So we're going to study this bigger system. But I can explain, you know, why this is not automatically going to tell us anything particularly good. And you ought to be a bit pessimistic, because I already told you what happens if you just add equations without compensating for that. You end up in one of the inner circles of hell. So we have to avoid that. So first of all, maybe you can write an exponential sum for that giant system, and it just fits on one line of the slide. And we're going to be interested in even moments of that sum. And I can tell you that because it corresponds to a translation-dilation invariant system, you can get optimal estimates for that giant mean value. But we have to take account of the fact that we added in these extra equations. You know, you don't get to do that for free. And so the natural way to do that is to do something like this. You know, you sort of sum over, just as we did with that value of h we had earlier, you sum over all the possible choices for the value somehow of those new polynomials that we added in, new equations that we added in. And maybe you have to do something as weak as the triangle inequality, and then you lose a factor of 6 from doing this. It's quite inefficient. And so you're certainly not getting square root cancellation. And for the case that we need it, that would actually be slightly worse than trivial. only by a factor x to the epsilon, but still, it doesn't make you feel optimistic, does it? So we're going to do something a bit different. And this, to me, when I first realized this was possible, was unexpected. It's kind of fun. So one observation about this system is that it contains a cubic Vinogradov system, right? And we have a number of variables which, in which we know that the number of choices for Z1 up to Z12 is bounded above roughly by x to the 6 plus epsilon on this Vinogradov estimate. It's an optimal estimate. So, so that's pretty good. I mean, you could do the thought experiment of thinking of what kind of lower bound you could prove for this system. And if I just set Z1 equal to Z7 and Z2 equal to Z8 and so on, there are x to the 6 choices for Z which satisfy those conditions. And so the number of choices that we can prove there are for Z's is not that much different from the lower bound which you can achieve. So in this system, let's just set Z1 equal to Z7, Z2 equal to Z8 and so on, and just see what happens. You know, what the hell? Yeah, since we're risking going to one of these circles. Okay, so if I do that, let's just follow what happens in one of these equations which involves h's, say the quadratic equation. If Z1 is equal to Z7, then I can pull the first term on the right-hand side over to the left-hand side. I get h1 minus h7 times Z1 squared, h2 minus h8 times Z2 squared, and so on. Now I'll just relabel that. So all I've done is I've labeled those differences between the z's as g's, and I've just tracked what's happened there. That's the same system of equations with that specialization. And the key observation is that for each possible choice of gi, there are roughly capital X choices for H1 or for the H's which give that G. So capital X choices for H1 and H7 whose difference is G1. Similarly for the other choices of variables there. So now we're in the situation where this giant system that we started off with, we made some specializations to get a lower bound. There are X choices for each of these G's, so X to the 6 choices for the G's altogether, given the H's. So a lower bound for this giant mean value is X to the 6 times this mean value, which was actually the one we're interested in, right? That's exactly the system that we were interested in bounding. And I'm claiming that with efficient congruencing or decoupling methods, you can get an upper bound for this giant mean value, which is optimal, X to the 12 plus epsilon. So what we just did was prove the optimal mean value for K, the thing we're interested in. So what happened there was that we had a non-translation-dilation invariant system, and you can view this in a couple of ways. You could either imagine that we kind of blew this up to this bigger system, which is actually translation-dilation invariant, and that allowed us in that system to work in such a way that we were able to extract the optimal estimate. Another way I like to think about it is that we've got this enveloping system which captures all of the information about our non-translation dilation invariant system. And we're capturing the solutions with a multiplicity, which again recaptures the optimal upper bound. So both of these viewpoints are useful, I think. The reason why this works is because in this system, which we're really interested in, we've got linearity with respect to one of the variables. But so what? I mean, if we have linearity, we should use it. Okay, so that's kind of the the idea of it extends, of course, to any degrees you like. So just to continue the train of thought, if you use this optimal estimate, then in our application of Holder's inequality, you get exactly what I was claiming. Good. Okay, so I wanted to give some ideas about what goes on with efficient congruencing and also get to this function field aspect, which I will try to do at a slightly higher velocity, but it's kind of impressionistic, so I don't think it matters too much. So first of all, to give some kind of idea of what's going on in efficient congruencing. So this is all a cartoon. You don't need to worry about any of the details here. Let me just say we're going to be interested in an exponential sum. I put in weights because I can, and it's actually useful. Imagine that these phis are polynomials which satisfy this non-vanishing Wronskian condition. And for reasons that become apparent, I picked a prime p, and I'm interested in particular in what happens in arithmetic progressions C modulo p to the h, different powers of p. And because of a non-vanishing Wronskian condition, there's really no loss of generality in supposing that these phi-j's p-adically are approximately t to the j. So they're sort of approximating a Vinogradov, approximated by a Vinogradov system p-adically. And
Going to fix p?
I'll fix p for the argument. You can choose any p you like, but fix p. And there's some kind of notion of an integral. It's really a discrete sum, a discrete approximation to an integral, but it's a sort of a mod p to the b animal, where b is very large. So none of the details really matter, right? So it's just me trying to be a little bit honest about what's going on. And the upshot of efficient congruencing is, I think I should do that, is sort of a mean value for the exponential sum where you're not restricted in terms of any arithmetic progressions, so you're really summing over all integers, in some kind of weighted average of what goes on in arithmetic progressions C modulo p to the h. So just to give something which is a bit easier to assimilate, what's going on the right-hand side, on the left-hand side, sorry, is that I'm counting all solutions of congruences mod p to the b, where I'm not restricting the variables at all. It's a weighted sum, weighted average, weighted count of solutions. And on the right-hand side, I've got something kind of similar. But what's important is that the variables underlying the mean value are all constrained to the same arithmetic progression C modulo p to the h. And I'm averaging over those progressions with appropriate weights. So you can think of this in a couple of ways, as I try to do here. So either you're kind of concentrating the solutions towards the diagonal almost for free. There's a loss of p to the h epsilon, or you're arranging that the congruence classes modulo p to the h don't really see each other. So it's sort of an almost orthogonality relation there. And other parameters here. So S is going up to k times k plus 1 over 2. And capital H is b over k. So the bigger H is, but the bigger the constraint. So I have to limit this constraint to be at most b over k. K is the number of independent polynomials. And S can't be any bigger than k times k plus 1 over 2 for this to work. That's the number of independent polynomials is k. So, this is roughly what's going on with this efficient congruencing idea. Something similar in the decoupling world. And a number of years ago, although we've not published this, Kevin Hughes and I sort of really worked out a decoupling interpretation of this. And so maybe, this is a picture, right? So you won't see another picture in the talk, in case you're wondering. So somehow over here, we've got all these mod p to the b congruence classes that are underlying this exponential sum. And you're able to bound this in terms of what's going on, where the mean value only cares about what goes on mod p to the h. So it's a sort of globs of congruence classes that interact with each other, but the respective globs don't talk to each other at all. That's kind of the gist of all this. And just to give you an idea of where the translation-dilation invariance comes into all this, so this is a bit risky because it's, we'll give it a go anyway. So what's important for auxiliary mean values which crop up in the argument, and this on some level goes all the way back to Vinogradov and Linux actually. So you have mixed mean values. So the important thing here is there are two congruence classes, C modulo P to the A and eta modulo P to the B, and you kind of see that more or less anyway in this interpretation of this mean value. We're counting solutions mod P to the B of a system of equations, which looks like a Vinogradov system actually. And, you know, translation invariance, what does that do for me? Well, I can translate all of these variables by this residue eta. So that's an application of a binomial expansion, really. So if I translate backwards by eta, all of the variables here get shifted backwards by eta. And over here, well, the etas disappear, and I've pulled out the powers of p to the b in front of the sum here. So already, this looks like an interesting maneuver because we started out with constraints modulo p to the beta in the original problem, p to the b, sorry. And over here, we've got constraints modulo p to the jb. J, of course, can be much bigger than b. And that was already observed by Vinogradov and Linux in some form. Vinogradov was looking at real short intervals and Linux with congruence classes. And there's a special interpretation. So in the original system we were looking at, there's this constraint which applies throughout. There's a constraint modulo p to the jb on a subset of the variables. And I can make the brilliant observation that I can throw away some of these congruences if I like. I just felt like doing that. And I threw away enough so that I've actually got a system of R congruences in a total of R times L plus 1 variables here. And all of them apply to a power of P which is at least as big as K minus R plus 1 times B. So that is an approximately Vinogradov type system of equations of congruences to a fairly large power of P. And I can use some kind of inductive strategy to, because R is smaller than K, I can inductively try to understand these. And so what the upshot will be that I can more or less assume that the X's and Y's are all in the same congruence class modulo p to the k minus r plus 1 b over r. So that means that I've created this extra congruence condition, which I can recycle with the same kind of strategy. So that's kind of at the core of this efficient congruencing approach. Okay, so finally I can tell you a bit about function theory approach. Yeah.
Does your method, your new result, which translation-dilation invariant, apply to some of these decouplings where they're trying to understand sharp decouplings, which that Bourgain was looking at?
Yeah, I mean, so
you looked
the decoupling results.
They're not, so in situations where they're trying to get it sharp where it isn't because they don't have translation.
Yeah, so I think so in the most interesting parts of the decoupling problems, which we're interested in, they would have discrete sets of real points. And so for this, my view is that this is really an analytic problem. I mean, it's similar problems in the p-adic situation as well. But with these methods that I'm using, I'm actually using a bit of number theory. So I'm using the fact that these sets that I'm looking at, which are integers, are translation invariant. If I shift the set of integers by a fixed integer, you still get the set of integers back again. That's not the case if you've got discrete sets of points. And somehow the decoupling methods and the basic efficient congruencing methods don't care whether you're looking at discrete sets of points or the integers. So there's a sort of fundamental difference there in what's going on. I mean, there are philosophical issues which one has to address. Okay, so quickly on the function field side. So I'm going to try to look at the two-dimensional system as fundamental in a sort of funny function field world, right? So not FQ of t, this is really z of t modulo some monic irreducible polynomial, not necessarily irreducible. And as a toy example, I'll look at the qubit case again. And I'm just going to look at this system of equations in xi plus yi modulo t squared, right? Not very hard. And if I just reduce mod t squared, right, what happens? Well, I can expand. I use a binomial theorem. You could do this in kindergarten, right? So expand, and you throw away anything involving t squared. That's what I just did there. But now, you see, if I look at the coefficient of t here in this system, then I get these equations involving xi squared yi and xi yi and yi. They all have to match. And the coefficients of t to the 0, otherwise known as 1, I get a Vinogradov system involving xi cubed, xi squared, and xi. Okay, so the number of solutions of this system of congruences mod t squared with the variables in a box of size x is actually exactly the same system that we were looking at earlier when we just were thinking about giant systems of equations. So that suggests trying to actually think about efficient congruencing in this function field setting. And I can see I've got 5 minutes left. I think, okay, I'll give this a go. So what lies at the basis of the induction in efficient congruencing is just a linear result. And this is really Newton's method or Hensel's lemma in one variable. Earlier versions used multivariable Hensel's lemma, but this is just a one variable version. And one interpretation of Hensel's lemma is the following. This is this claim here, which maybe I'll push straight on to the next slide. So as long as I've got a polynomial which has a non-vanishing derivative at the residue c modulo p, then there's a way to refine congruences. So if I've got a congruence phi of c plus p to the ax, congruent to phi of c plus p to the ay modulo p to the b, then these variables themselves, at least the shifted versions of these variables, have to match modulo p to the b. And, I can, so sort of a two-line proof almost. You just consider a Taylor expansion. So I write down my Taylor expansion for each side of the congruence here. All of these coefficients are integers, by the way. The phi of c terms vanish. There's a p to the a term, which I can also cancel through. So the derivative phi prime of c times x has to be congruent to phi prime of c times y. Well, modulo p to the a, but maybe a is so big that actually capital B minus a is too small somehow. You see, that means, that means that x has to be congruent to y modulo p to the a, that's with too big. And I could have used that information right at the beginning to refine what I started with. So if I just iterate this, I find that I get cut off when my a is too big here. So I could have replaced a by 2a right at the beginning of this all. And And then I would get the conclusion, right? So just iterate. It's the same, same Hensel's lemma. If you know Hensel's lemma, then it's not even a disguise. You know that this is the case. Okay, so what about this function field setting? So we're going to try and do the same thing. And if you're super smart, if you're smart, then you know already what's going to happen. I can see some smart people in the audience already. So, let's go through the same kind of story. So now my residue class is actually going to be a linear polynomial in T, which I'm reducing modulo power of P, right? Now I'm going to assume that the derivative does take the shape mu plus mu T mod T squared, but I'm going to insist that mu and P are coprime. So this will actually make this a unit in this ring which we're looking at synchronously. So then what I claim is that whenever I have the same kind of congruence that I had before, modulo the ideal generated by T squared and P to the B, then in fact the arguments have to be congruent to each other modulo the same ideal. And this is another instance of Hensel's lemma, in fact, although the one you don't learn in kindergarten. So let's just see how that goes. Same argument as before, right? And what's important to us is that if P to the A mu plus nu T times U is congruent to P to the A mu plus nu T times V, we'd like to deduce that U and V are congruent to each other modulo an ideal generated by T squared in a power of P. And I need to find an inverse for mu plus nu T. But if you multiply by mu minus nu T, then you get mu squared minus u squared T squared, and modulo T squared, that's just mu squared, isn't it? So you can find the inverse easily enough. So in fact, you find that U and V are congruent to each other, modulo this ideal generated by T squared and a similar power of P as the one we were looking at before. So repeat, right? So that, in a nested way, is what underlies the nested efficient congruencing method in this ring setting. Sort of the first instance of looking at this really in a higher rank module. Okay, so the upshot of this is that this applies quite nicely to generate even generalizations of the result that I was looking at before. You have some set of polynomials that have non-vanishing Wronskian, then these linear coefficients, you get optimal estimates for the mean values, those that match the main conjecture. And again, that's a new instance actually of a system of equations which are not translation, dilation, invariant, but get optimal estimates for. Okay, so that's that. Yes, thank you. Right.
Questions?
So you go to the zero-free region for the Dirichlet functions with powerful conductor. I assume you couldn't do Vinogradov. Not for prime, not for. Yeah, that's very hard. In other words, to get the zero-free region, which is better than other model of a local sign.
Postelnikov. So Henry,
Powerful, yeah. But I'm asking whether your methods in that setting. So your methods of efficient congruencing or decoupling don't control there's the epsilon that you gain, and then the dependence in the K is terrible.
Yeah.
But I'm asking if in the other situation there's anything better, you know?
So
which would be more closer to your p-adic method problems.
Yeah, I mean,
you would take powerful conductor P to a power, yeah.
I mean, Okay, so
I'm just trying to understand that.
two parts of
Yeah.
your answer here. So one is zero free regions of zeta and L functions. I am absolutely convinced that improvements in all these mean values have zero impact.
No, are you sure as well in the other case?
And I can tell you why, and I could explain at greater length, which nobody would want to hear. But you can see visibly lower bounds for these mean values, which if you just assume they were actually the upper bounds, so that's a great leap of faith, you still make no improvement to what's going on. You know, the dependence on K is genuinely there, and so that kind of corrupts everything. But these sort of the sufficient congruencing idea does actually give you new estimates for certain character sums, where the characters have very powerful moduli. Because from the point of view of a method, it doesn't really care whether you're looking at exponential sums or character sums, you can still make everything, you still get these concentration arguments and so on. So in that sense, it's a natural setting. It wants to work in a p-adic setting. And really the difference between the methods is, you know, if you've got a problem which is inherently about real numbers, you want to use a decoupling method. If it's to do with integers, you can make your choice because you can work in a real or a p-adic place. And if it's inherently about sort of congruential or p-adic problems, then you want to work with efficient congruencing.
We thank Trevor again.